These are the materials required to build a self-balancing robot. So this one, I'm gonna put the battery here, like that. Let's go. Boom. The first step is to solder both DC motors with their respective wires. Next, we attach the battery holder to the frame using a screwdriver. So, here is the final output. Sheesh. Isa. Let's go. 10 seconds. We then mount both motors on either side of the frame alongside the battery holder, securing them with screw and nuts. After that, we connect the first layer of the frame to the support pillars, which hold the second layer for the motor driver and MPU 6050. motor driver regulates the power and direction supplied to the motors, while the MPU6050 is a gyroscope and accelerometer sensor that continuously detects the robot's tilt and orientation. Both are essential for keeping the robot balanced.
Before securing the second layer, we soldered the MPU6050 with its I2C connection module. This step proved to be particularly challenging, as the MPU6050 chip is extremely small and requires precise, careful soldering technique. During the process, the I2C module was accidentally damaged. Fortunately, we had a spare on hand, which allowed us to continue without a delay. Once the I2C connection was successfully soldered, we proceeded to attach the third layer of the frame, which houses the Arduino Uno R3 secured with a screwdriver.
The Arduino Uno R3 serves as the brain of the robot. It processes the sensor data from the MPU6050 and sends commands to the motor driver in real time, executing the PID control algorithm that keeps the robot upright.
With the Arduino in place, we assembled all three layers together, noting that the second layer already had the MPU 6050 and the motor driver installed prior to final assembly. We then attached the wheels to the DC motors, completing the physical build of the robot. And there it is, a fully assembled self-balancing robot. The next phase involves connecting all components according to the circuit diagram, followed by uploading the control code through the Arduino IDE. Here's the circuit diagram that we will attach through its components. And here are the codes for the Arduino R3. At first, the wiring process was quite confusing as there were multiple components to connect, and it was easy to mix up with the connections. However, by carefully following the circuit diagram step by step, we were able to wire everything correctly. Here is our working self-balancing robot. Although it took many attempts to troubleshoot and resolve unexpected errors along the way, we were able to get it fully functional. The challenges we encountered throughout the build taught us a great deal about patience, precision, and problem solving.
Guys, nagtawa guys, naigibaon na balancing robot guys. Tawa guys. Ah! Sikrikan sa guys. Kabate na robot tayo. 7 seconds. In this video, we watch a small robot, just a foam board, motors, and a tiny sensor, learn to stand upright on two wheels. It wobbles, it overrocks, and then slowly it finds its balance. That little robot uses something called a PID controller. It constantly reads where it is, compare that to where it should be, and make a small adjustment over and over again. And honestly, that's not so different from us.
We all have moments where we feel off balance, leaning too far one way, overcorrecting the other. But balance isn't a destination you arrived at. So it's something you keep working toward through constant, like small adjustments. So the robot doesn't give up when it tips over, so it just recalibrates and tries again. So here's a question. Where in your life do you need to recalibrate right now? What small adjustments, not just a dramatic change, just a small one, Or could you move closer to the balance you're looking for? So I hope these questions answers how it reflects ourselves on balancing our life just as self-balancing robot do. So thank you for watching on our self-balancing robot. And thank you.